Hello viewers, welcome to the three-phase circuits. That is what is today's topic. So far we have seen in AC circuits, it was single phase circuits. We dealt with RL circuit, RC circuit, RLC series circuit, and then RLC parallel circuit. Okay, so this is three-phase circuits. What do you mean by three-phase circuits? Basically is when you can see over here, this is what is called as single phase supply. You can see only one wave over here. Now in this 360 degrees, if we have three phases like this, so one phase is like this, another phase is like this, and another phase is like this. So in 360 degrees you have three phases. That means 120 degrees, 120 degrees, 120 degrees, they are apart. Okay, so phase 1, after 120 degrees it is phase 2, and still after 120 degrees it is phase 3. You can see the phase difference of starting. You can see the phase difference in the peaks also. Okay, so that is 120 degrees, 120 degrees, 120 degrees. Now the specialty of three-phase supply basically is three-phase supply is as good as you are having three single-phase supplies. Okay, normally single-phase supply is given to residential loads, and the industrial loads are supplied by three-phase supply. Okay, so this is what is actually three-phase supply. Now why don't we have three single-phase supplies rather than three-phase supply? The answers are like bit complex, but I can tell you in few points. Like for the same size of machine, you can have the size of the machine, may it be generator or a motor, it will have output almost 1.5 times the single phase one. The second thing is while transmitting a given amount of power at a given voltage over a specified distance, the three-phase transmission line requires less material like copper or aluminum, whichever is used, than single phase. The reason behind it is simple. When you use three single phase, it will be two lines, one live and one neutral for these three, right? So phase neutral, phase neutral, phase neutral. So likewise you will have 6 wires. Okay, in case of when we talk about three phase, it will be having 3 line terminals and 1 neutral, so it will be R, Y, B and N. Only 4 wires will be required. Okay, so that is just to give you an example. So what is seen is that the material required in case of three phase supply, three phase is quite less than whatever if we use single phase for the same thing. Okay, the third point is the three-phase motors have got uniform torque, whereas the single-phase motors have got pulsating torque. Okay, the torque is not constant, it is not uniform, but it is pulsating. Okay, so that is not a good feature actually. The last one is single-phase motors are not self-starting, whereas three-phase motors are self-starting. Okay, so these were few advantages of three-phase system, why we go for three-phase system and like that. Okay, now one more question that can come into your mind is why not then 5 phase, why not then 7 phase, 9 phase and so on. We can have a number of phases more, but if you see that there will be many complications if we go for 5, 7, 9 like that. Okay, so it is universally followed, the system is actually three-phase system. Okay, but researches are going on in 5-phase motors and 7-phase motors and 9-phase motors as well, but still it is in research mode only, and what is universally adopted is a three-phase system. Okay, so let us stick to this and we'll be seeing what are these three-phase systems. Okay, naming of the phases, when we talk about these three phases, the three phases are 120 degrees apart, as I have already said through this diagram, if you remember. Okay, so when I talk about this, they have got phase differences of 120 degrees, but they have equal magnitude. You can see over here their peak is coinciding. Okay, so they have magnitude wise they are absolutely the same, but what is the difference is the difference is in the phase. Okay, so this is how R phase starts, then 120 degrees it is second phase, and then still 120 degrees it is the third phase. Okay, so another way to put it up is if at all it is single phase, it is like this. Now this 360 degrees when are contributed by 3, it will be 360 divided by 3, so that will be 120. So 120, 120, 120. Okay, so that is how you can put it. This is how you can show it over here. This is one phase. Let us say it is VR. Then after 120 degrees it is Vy, and still after 120 degrees it is Vc. Okay, so if I write this as V at an angle 0, the first phase, the second phase can be written as V at an angle minus 120. Okay, since magnitude is same, I'm writing it as writing it as again V, isn't it? Again over here when I talk about third phase, it will be V at an angle minus 240. Of course minus 240 can also be written as plus 120, है ना? Whatever is 240 degrees lagging is 120 degrees ahead actually, isn't it? We are talking about anti-clockwise sense. Again let me tell you, remind it of. Okay, so you can see over here is this is your first phase, and it is having voltage as root 2 V sine omega t into sine omega t, that is volts. This V stands for volts. Okay, so VA at an angle VA is equal to V at an angle 0. Okay, why this root 2 V? Because this peak is, let us say, V. Okay, so to find out the value of the RMS value is V, so this maximum value is root 2 V. Okay, because how do we write voltage equations, current equations? Remember, V is equal to Vm sine omega t. Okay, so here the value we need is maximum value. Okay, so if the RMS value is V, the maximum value will be root 2 times V, isn't it? Yes. So VA can be written as, that means first phase voltage can be written as V at an angle 0. Second phase voltage can be written as same, the magnitude will be remaining same. Now the angle will be, the phase difference minus 120 will be added to this. Okay, so it will be in polar, if you want to write it, you will be writing it as V at an angle minus 120. Okay, similarly the third phase voltage, it will be root 2 V sine of omega t minus 240. Okay, or you can write it as V at an angle minus 240. Okay, so magnitude V and angle minus 240. This can as well be written as V at an angle plus 120, right? And this V stands for volts. Okay, now these three phases are 120 degrees apart, so I can write VR as Vm sin omega t, Vy as Vm sin omega t minus 120, and Vb as Vm sin omega t minus 240, or I can write it as Vm sin omega t plus 120. Okay, there is something what is called as phase sequence. Okay, so the sequence in which the phase voltage reach their maximum positive values is what is called as phase sequence. You can also define it in terms of the starting. Okay, so you can see this is the first phase which is starting, then it is the second phase which is starting, and then this is third phase. Okay, so here the sequence is A, B, C, right? So A is reaching maximum first, then B is reaching maximum, and then C is reaching maximum. Okay, so you can either define it in terms of reaching to the positive maximum, or you can define it in terms of starting. Okay, one and the same thing, right? Even if you define it in terms of starting, it is the phase difference of 120 degrees between the three phases. Even if you define in terms of the positive peaks, it is again 120 degrees difference, isn't it? Okay, so this is the sequence in which the phases attain their positive maximum values, or it is a sequence in which the phases start. Okay, so that is what is called as phase sequence. This phase sequence is very important. You can see over here, this is R, then 120 degrees behind it is Y, and still 120 degrees behind it is B. Okay, so R, Y, B. Okay, I'm not writing it here as R and this over here Y. If I write it over here Y, it means plus 120. Is it plus 120? No. I want to show that VY is 120 degrees lagging. So in that case, I'll have to show Y over here. Am I clear? Okay, so that is what is meant by phase sequence. Okay, so VR, if at all drawn in Y-axis, 120 degrees behind it will be VY, and still 120 degrees behind it will be VB. Okay, so that in the anti-clockwise sense, VY has got VR is 120 degrees ahead than VY, and VB you can see R is 240 degrees ahead than B, isn't it? Okay, so that is how you put it, because VR is Vm sin omega t, Vy is Vm sin omega t minus 120, and Vb is Vm sin omega t minus 240. So that is how you account it for, right? So this is VR, this is Y, and this is B. Okay, so mind well, the phase sequence has to be always correct. Okay, yes. The next thing is why am I elaborating on this phase sequence? Phase sequence is very important as far as parallel operation of generators are concerned. That means when you want to run two generators in parallel, the phase sequence has to be clearly followed. If one thing is RYB, another should be also RYB. Otherwise, it will be erroneous operation and it will be a major fault. Okay. Secondly, again parallel operation of transformers. I suppose you have gone through single phase transformers, but over here I'm talking about three phase transformers basically. Okay. So again RYB of the first transformer and the second one, which is to be connected in parallel, should be having the same phase sequence. Okay. And the last one is direction of rotation of motors. So if at all one motor is running in one direction and others phase sequence is wrong, in that case it will be running in the opposite direction. Okay. So you'll have to this phase sequence has direct impact on the direction of rotation of motors. Okay. Let me discuss one more concept over here, what is called as balance load. Now what do you mean by balance load? Basically is when the three phases have got the same load, we call it as balance load. Practically speaking, it is not at all feasible to have a balance load, but since we are in a very preliminary phase, I am going to talk about balance load only. Okay, but practically speaking, you cannot have a balance load on a system. Just to give you an example, you know, you have society transformers outside your society. Okay, from there you can see if there are three buildings in your premises, to one three phase supply is you take from the transformer. Rn goes to, let us say, A building, Yn goes to, let us say, B building, and Bn goes to, let us say, third building. In this case, it can happen that because of phase failure, one of the building is like dark completely, and the two are healthy, and still the load is on. Okay, so in this case you cannot have a balance load, right? Secondly, you cannot say that all these three buildings will be having the same load. Okay, you cannot even forget about the buildings, you cannot say that the two houses are having same loads. Okay, so it may be a case that one house is having all the rooms air conditioned, and let us say the neighbor is having no AC. Okay, so there will be a large difference between the consumption, right? So that, just to give you an example, that practically to have a balance load is not feasible, but just because I'm putting a concept of three phase loads right now, I'll have to talk about balance load. Okay, so balance load means each phase is going to have the same load, exactly the same load. Okay, so the all the phases will be having this Z, you can see over here, this is Z angle theta, this is Z angle theta, this is Z angle theta. So every phase has got the same load, every phase has got the same load. Okay, so that is what is meant by balance load. Okay, you can see over here. Of course, one more thing is, now you can see over here is I have shown the directions of IR, IY and IB, like feeding to the load, right? Now this is if at all I'm talking about three phase generator. Okay, what do you mean by generator? It is supplying the load. Okay, now if I talk about three phase load, in this case the direction of this current will be exactly opposite. Okay, so just because here I am showing the generators, it is the direction of the current shown like this. Okay, the next thing is, yes, you can see over here when I talk about the three phase systems, there can be two ways. One is what is called as star connected system, and another is what is called as delta connected system. Okay, so you can see over here, this is what is star connected and this is what is delta connected system. Okay, how a star is connected, you can see over here, if these three coils are there, and if all these three ends are connected and rest of the three ends are open for the connections, this is what is called as star connection. Okay, you can see over here there is a common point between the three coils. This is what is called as neutral connection. Okay, and this is delta, where you can see the starting point is connected to the ending point of other, starting point of one is connected to ending point of other, starting point of one is connected to ending point of other. Okay, so this is what is called as mesh connection or delta connection. This you can show it like this, so this becomes a star, and this, when you show it like this becomes a delta. Okay, so delta connection is also called as mesh connection or loop connection. Okay, you can see over here from the neutral you can draw one more wire over here, and that will be neutral. Okay, so this is also called as three phase 4-wire system, and this is three phase 3-wire system. Okay, you can see over here the fourth wire is coming from neutral, and three are the line terminals. Okay, so that is why three phase 4-wire system is basically the star connected system. Okay, and as far as delta is concerned, you can see it is 3-phase 3-wire system, because it can there are 3 vertices of the delta, so only 3 wires can come out, so that is a 3-phase 3-wire system. Okay, now when I talk about 3-phase systems, there is one more concept, is what is called as phase values and line values. Okay, now what do you mean by phase values? Is when I am talking about these 3 phases, that is the value which is phase value, and when I talk about these line terminals, this is what is called as line value. That means current entering from here will be line value, current entering in the phase will be a phase value. Okay, voltage tapped across these line terminals will be line voltages, and voltages tapped across the phases will be phase voltages. The phases will be phase voltages. Okay, similarly over here you can see the voltage tapped between R and Y will be phase voltage. Okay, the current entering from this will be the line current, and you can see the current which is flowing through the phase, you can see over here it will be a circulating current, so the current which is flowing through the phase will be phase current. The current flowing through the phase will be phase current. Okay, so I hope the idea of phase and line is clear to you. Okay, so when I talk about line terminals, may it be voltage, may it be the current, it will be line voltage or line current. When I talk about the currents into these phases or voltages across these phases, I call it as phase voltages or phase currents. Okay, now let us talk about phase voltages first, star connection first. In the star connection, you can see over here, this is that star, okay, and that is feeding to the load. Okay, so you can see over here IR, IY and IB. Okay, these are line currents. Okay, and you can see over here this is the phase current is same as the line current. This is the phase current which is same as the line current. This is the phase current which is same as the line current. Okay, but if you tap the voltage between R and Y, these two, is it same as whatever is across this or across this? No, you'll have to apply KVL, right? So RY will be equal to whatever is R minus Y. Okay, so R minus Y will give you RY. Okay, if I talk about YB, it will be Y minus B. Okay, since this is neutral, it is normally not mentioned as Yn, Rn or Bn. Okay, so instead of N we just write it as Vr, instead of Vyn we just write Vy, and instead of Vbn we just write Vb. Okay, so what does Vr, Vy and Vb stands for? It is the phase voltage. And what does Vry stands for? It's a line value, line voltage. It is Vyb, again it's a line voltage, and it is Vbr, that is again a line voltage. Okay, so you can see from the diagram that phase current is equal to line current, but for finding out the relation between phase voltage and line voltage, will I have to apply KVL. And what is that KVL basically is? That will be Vry is equal to Vr minus Vy, Vyb is equal to Vy minus Vb, and Vbr is equal to Vb minus Vr. Okay, you can see over here in the phasor diagram, I can draw Vr 120 degrees behind, I will be showing Vy, still 120 degrees behind, I will be showing Vbn. Okay, understood? So what I did is Vrn, Vyn and Vbn are shown 120 degrees apart. Okay, then what you have to do is I have to show that Vr minus Vy is going to be Vry. Okay, I have Vy, so what will I do is in the opposite direction but of the same magnitude, so that will be minus Vy. Okay, so Vr minus Vy is going to give me Vry. Similarly, for Yb, Vy is there. What will I do is minus Vb I want, so I'll be extending this in the negative direction. Okay, of the same magnitude. Okay, and added to it on the parallelogram, the diagonal is going to give me the line value. Similarly, when I talk about Br, it is B minus R. So Vb I already have, minus Vr I can find it out by extending this in the negative direction for the same magnitude. Okay, and if I complete this parallelogram, I'll be getting that diagonal, or I can say the resultant as Vbr, that's the line value. Okay, now if you just consider only one parallelogram, okay, if you just consider one parallelogram like this, you can have Vrn, okay, minus Vy, and that gives you Ry. If you drop a perpendicular from this on this, the parallelogram property is it bisects. Okay, now since when you talked about the phase values 120 degrees apart, when it was negative phase voltage drawn, it became 60 degrees, and when the resultant was drawn, it became 30 degree. The angle became 30 degrees, right? So you can see this angle is 30 degrees. Okay, so when I drop over here the perpendicular, this particular part will be VPH cos 30, where this I am writing it as phase value. Okay, so instead of writing it as VR, VY or VB or VRN, VYN, VBN, I'm writing it as VPH. Okay, suffix PH says that it's a phase value. Okay, so when I drop a perpendicular on this, it bisects. So this much part will be equal to VPH cos 30, and again this much part will be equal to VPH cos 30, because it is equal, right? It bisects, the perpendicular bisects. Okay, so this line value is going to be twice of VPH cos 30. Okay, so VL is equal to twice of VPH cos 30. Now if I substitute cos 30 as root 3 by 2, what do I get? I get an expression as line value of the phase line value of the voltage is equal to root 3 times the phase voltage. Okay, now let us talk about power also. 3-phase power is equal to 3 times per phase power. Okay, so it will be 3 times VPH IPH cos phi. Okay, so it will be thrice VPH will be equal to now VL by root 3, as we have seen over here just now. Okay, so VPH will be equal to VL by root 3, right? So over here we put it as VPH as VL by root 3. In star connected networks, we have IPH is equal to IL. Remember I told you from the diagram. Okay, into cos phi. Okay, so that comes out to be root 3 VLIL cos phi. So if you put it in terms of phase values, it is thrice of VPH IPH cos phi, and if you put it in terms of line values, it is root 3 VLIL cos phi. Okay, so phase current vector will be drawn as per the load connected. What do I mean by this is, you can see over here we had drawn this phase voltages VR, VY and VB 120 degrees apart. Okay, so depending on whether it is lagging load or leading load or resistive load, the current will be drawn. Over here you can see IR I have shown lagging behind by a certain angle. So this over here I have considered a lagging load, which is normally a case. You can see 95% of the loads are inductive loads. Okay, so IR, that means the phase current is lagging behind the phase voltage. Okay, similarly IY is shown lagging behind, similarly IB is shown lagging behind. Okay, so that is how this is done. Okay, yes, so that was about the load current. Yes, so if at all it is resistive load, IPH will be in phase with VPH. If it is inductive load, IPH will be lagging VPH, and if it is capacitive load, IPH will be leading the VPH. Okay, let us deal with few solved problems so that the ideas will be better clear in your mind. The first problem is the phase voltage of a 3-phase 12 MVA star connected alternator is 6 kV. Okay, calculate the line voltage and full load line current. Okay, the very first thing is, since it is star connected, line voltage will be equal to root 3 times phase voltage. Okay, you have been given phase voltage, right? So it will be root 3 times the phase value, and that will be 10.3923 kV. Okay, again point to be remembered over here is, we are going to round it off after 4th decimal. Okay, the rule being absolutely the same. If at all 5th decimal point place is greater than 5 or equal to 5, we'll be adding 1 to the 4th one. Okay, if it is less than 5, we'll be just treating it up to 4th decimal. Okay, yes, the next one is, you have been given MVA rating. Okay, what is MVA actually? It is 12 into 10 to the power 6 volt amperes. Okay, now volt amperes, when it was single phase, it was simply V into I, but when we talk about 3-phase power, it will be either thrice of VPH IPH or it will be root 3 VLIL. Okay, so if you put it in terms of phase, it will be thrice of VPH IPH, and if you put it in terms of, let us say, line, it will be root 3 VLIL. Okay, so you can see over here 12 into 10 to the power 6 is equal to thrice of VPH IPH, that is equal to root 3 VLIL. Okay, so this way you can find it out what is IPH. Okay, since it is star connected, IPH will be equal to IL. Okay, that is it. So that was the first problem. Second one is, 3 equal impedances are connected to 3-phase 400 volt 50 Hz supply. If the inductive reactance and resistance of each branch are 8 and 6 respectively, find IL and power consumed. Okay, so very first thing you have to find it out is, you have been given per phase impedances. Okay, so ZPH is equal to, now inductive reactance is given as 8, and resistance is given as 6. Okay, so it will be 6 plus j8 ohms. Okay, you can convert this 6 plus j8 into polar form as 10 at an angle 53.13. Okay, then IPH will be equal to VPH upon ZPH. Now what is VPH value? See, unless and until specifically mentioned, always the given value will be taken as line value. You can see in the first problem it was specifically mentioned, it was phase value, so we took this as phase value. Okay, but over here, is it mentioned anywhere that it is line value or phase value? No. So you will be treating this value as line value. Okay, if you remember in AC fundamentals, I had told you the same monologue as unless and until specifically mentioned, always the given value will be RMS value. In three-phase circuits, the same monologue now will be converted into that unless and until specifically mentioned, always the given value will be a line value. Okay, so taking this as line value, the phase value will be 400 by root 3. Okay, and divided by, it will be ZPH, that is 10 at an angle 53.13. See, this is the division, so I wanted ZPH in terms of polar form, so I took it in polar form. Okay, so 400 divided by 10 by root 3 gives me 23.094. Okay, and the angle over here will be, nothing is given, that means 0, so 0 minus 53.13, so this angle becomes minus 53.13. Okay, since star connected, IL is equal to IPH, so it will be 23.094 at an angle 53.13. Okay, power consumed will be, either you can put it in terms of line or you can put it in terms of phases, so it will be thrice of VPH IPH cos phi, or you can write it as root 3 VLL cos phi. So this is the power. Okay, and the last problem is 3 similar coils connected in star, take a total power of this and this, power factor is this. From 400 volt 50 hertz supply, calculate R and L of each coil. Okay, so three-phase power is given to you. You can write it as thrice VPH IPH cos phi. Even cos phi is given to you, so you can find out what's the value of IPH. Okay, since star connected, IPH is equal to IL. Okay, ZPH can be found out as VPH upon IPH. You already have the value of IPH and you already have the value of VPH. Okay, since the given value will be always treated as line value, we have divided it by root 3 to get the phase value. Okay, so this is how the ZPH goes, and cos phi will be equal to R by Z, isn't it? So that comes out to be R will be now 4.2667. Okay, and similarly you can find it out what is the value of X. Okay, so by Z square is equal to R square plus XL square. This is one more numerical you can just go through. Okay, that's it for now. We'll see in the next lecture what is delta connected circuits. Okay, thank you.